Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. In this video, we're going to answer the question, what is polymorphism? You've come across this term in your study of object-oriented programming, and specifically once you got to inheritance. Let's look at an example that will illuminate this concept, and as a bonus, inheritance and dynamic binding as well. Let's imagine we want to write a racing simulation, and we invite different sorts of moving objects to participate. We will call them racers. Each racer will be able to calculate how far it moves in a round. If we have two cars, for example, they will use the same calculations to determine how far they move in a round. But if we have a bicycle, or a horse, or a rabbit, they will each use different calculations to determine how far they move in a round, because they all move very differently. In an object-oriented system, this is an opportunity for an inheritance hierarchy. We can have one superclass called racer. A racer will maintain its location, how far it's moved, and we will give it a move method. The move method will advance the racer's distance. So, for example, if a racer starts at 0, and it moves 1 unit every time we send it the move method, then if we send it the move method 3 times, it will be at location 3. But now we want to allow for different kinds of racers that will move according to their own specifications. We still want them to maintain their location, and we still want them to respond to the move message, but how they respond to the move message will depend on what kind of racer they are. If you're coming from a procedural programming background, you might be inclined to write an if statement. If I'm a car, move this way, else if I'm a bicycle, move this way, else if I'm a horse, etc. That inclination is a hint that you should write an inheritance hierarchy instead. We want to subclass racer. Let's imagine subclasses for car, horse, and bicycle. Each of those subclasses will have its own move method that is different from the generic move method in racer. So maybe when car is sent the move message, it advances 5 units, but when horse is sent the message, it only advances 3, and bicycle advances only 2. After 3 move messages, the car is at location 15, the horse is at location 9, and the bicycle is at location 6. We can send each the same message, but the way they respond to the message is unique to each subclass. I've drawn a class diagram for this inheritance hierarchy. The racer class is the superclass, and it contains the location field, the location of the object at some point while the program is running. And I have chosen to make that private. To modify that private field, the subclasses will need a method in the superclass. So I've added a protected advance method that they can use to add to the location field. A protected method can be invoked by subclasses, but it can't be seen outside of the inheritance hierarchy. The superclass also has a constructor, which takes no arguments and will simply initialize the location field to 0. Technically, we don't need that constructor, as location will automatically be given a default value of 0, but I wanted to make that explicit. It also has a move method, which moves the object according to its own mechanics, a getName method, and toString, which will return a string version of the object. There are then 3 subclasses, car, bicycle, and horse. Each of these have a getName method and a move method. I've made these intentionally quite simple. Obviously, they would be more interesting if they had properties that affected how they move. There's a difference between a Formula 1 race car and my old Honda, a plow horse and a Kentucky Derby winner, and a 3-speed bike and a racing bike. You can add whatever you want to this example to make the simulation more fun, but let's focus on polymorphism. Let's look at the implementation, and then we'll see where that polymorphism is. Here's the racer class, and for simplicity's sake, I've included no comments. You can see the private field position, and the constructor setting the field to 0. Then you can see the protected method advance, which adds the parameter amount to the position field. You can see move, which we expect to override in subclasses. This advances the racer by 1 unit. getName returns racer. Now, toString creates a string of dashes that is the length of position. So if the racer is at position 5, a string of 5 dashes, and then appends the name to the end of that. I'll run the program I've written so you can see what that looks like. You can see I've written a program that runs the race for 5 rounds, and at each round the car is pulling ahead of the horse and the bicycle, as visualized through the dashes. Let's look at the first subclass, car. The header is class car extends racer, which means the car is a subclass of racer. We also sometimes say a car is a racer, or a car is a child class of racer. The car object has 2 methods, move and getName, And for move, I simply have the car send the advance message to the superclass part of itself with an argument of 5, moving the car 5 units. For getName, it returns car. And if we look at horse, it's very similar. It advances 3 in response to the move message, and it returns horse as its name. I'll bet you can guess what the bicycle code looks like. It advances 2 in response to the move message, and it returns bicycle as its name. The mechanics of inheritance in Java can be confusing at first. Each of my subclasses, car, horse, and bicycle, extends the class racer. But what does that mean? When I create a car object, what do I get? Behind the scenes, Java allocates space in memory for all the fields declared in racer, along with any fields declared in car, if there are any. In this example, there aren't. Even though the position field is declared in racer, every car, horse, and bicycle object has its own copy of that field because it's part of the object's memory layout. However, because position is marked private, it can only be accessed directly by code inside the racer class. That's why our subclass's move method doesn't update the position field itself. It calls the advance method instead. Advance is defined in racer, where it's allowed to access the private position field directly. In this way, racer controls how its internal state is modified, while still allowing subclasses to affect that state by calling inherited methods. Now let's find that polymorphism. This is the race class, which creates objects from our inheritance hierarchy and runs the race you saw in the console. And here's the polymorphism on line 4. I'm creating an array of racer objects. Racer, open close square bracket, racers equals, and then I'm creating an array by putting objects inside curly braces. New car, new horse, new bicycle. Look closely at that. Do you notice anything weird? I've declared an array of type racer, meaning the objects in the array will be of type racer, but I'm putting a car, a horse, and a bicycle in the array. Let me show you 4 other versions of the array that would also be acceptable. I've given the arrays different names, so I won't have syntax errors. In Racers 2, I'm also including a car, a horse, and a bicycle, but in a different order. In Racers 3, I have 4 car objects. In Racers 4, I have a racer, a horse, and a bicycle. And in Racers 5, I have 2 racer objects and 2 car objects. The elements of the various racer arrays are polymorphic references. Polymorphic means many forms. The references can take on different types. They can morph or change. I could assign a new value to racers sub 0. I'll write racers sub 0 equals new horse. And if I run my program, now I have 2 horses running and no cars. The rules for a polymorphic reference are it can reference an object of any subclass of the declared type. The array is declared as an array of racer. So each element in the array can hold a racer object, but it may also hold any subclass of racer. Let's declare a single variable, racer the racer, and assign to it new horse. You can see that's fine. I can send it the move message. That's fine. Now let me assign to it a new bicycle. That's fine. The racer is a polymorphic reference, just like the references in the array. It can reference a racer object or an object of any subclass of racer. If tomorrow I want to extend this inheritance hierarchy by adding a bunny, I can put a bunny in this array and the program will run the race with a bunny. Maybe you'll take this program and you'll create a class of your favorite moving object, maybe a cat or an octopus or a Vespa. You can easily extend this system that I've created and with minimal changes add a whole new functionality. Now, I promised we'd talk about dynamic binding as well. Look at this loop. For racer, racer, racers, racer.move, and then system.out.println racer. What move method is going to be called? Look at my 5 different racer arrays. With the first array, the first time through the loop, the car move method is called. The second time through the loop, the horse move method is called, and the third time, the bicycle move method is called. But if we ran this loop on my Racers 2, then it would be horse, bicycle, car, and if we ran it on Racers 3, it would always invoke the car move method. Looking at the loop, we only know that the racer object being sent the move method is of class racer. But when the program runs, it might be a racer object, but it might be a subclass of racer. It's when the program runs that Java will determine which move method to invoke based on the actual class of that object, not the declared class. So if it's a car object, the car move method is executed. That's called dynamic binding. The word dynamic means this happens while the program is running, and the word binding refers to which code is bound to that call. So dynamic binding means that the correct code for that call is determined at runtime based on the actual type of the object stored in the variable racer. Let's walk through this loop in the debugger to illustrate. We'll work with the original racers list. I'll put a breakpoint to the right of racer.move, and we'll click the bug and we'll switch to the debug perspective. Now, we've stopped on the call to move. Let's look over in the variables area at racers. We can see it's an array of racer, but in location 0, we have a car. In location 1, we have a horse, and in location 2, we have a bicycle. And notice when I open them up, they each have a position field. Now, if we step into racer.move, we are in the car class, car.move. That's because the first racer is a car. I'll step return from that, and you can see now back in main that the car's position field is 5. If I hit go, now we're back at the breakpoint again, and this time our racer is of the horse class. If I step in, this time we're executing the horse move code. And when I step return, now the horse is at 3. So when I press go, and we're here again at move, now the racer object is of class bicycle, and when we step in, we're in the bicycle.move method. Step return, and now the bicycle is at 2. Let's summarize this. We're going to choose to create an inheritance hierarchy when we have a class of objects that are mostly the same, but need to behave differently in some circumstances. They might need to store information that is specific to their type, although we didn't do that here for simplicity. We'll create a superclass that has the common features of the different kinds of objects. And we'll give it the method or methods that will need to be specialized. In our example, the superclass is racer, and the move method is meant to be overridden. We'll then write subclasses for each class of object that needs to behave differently. And we'll override the method that implements that behavior. In our example, those classes are car, bicycle, and horse, and the method is our move method. At runtime, when a subclass object is created, the superclass data will be part of the object. But if the data is private, the subclass methods won't be able to directly access the data. When we have a variable reference of the superclass type, we can assign an object of the superclass type to that reference, or we can assign any subclass object to that reference. That is called a polymorphic reference. In our race program, we have an array of racer objects that contains objects of all of the subclass types. We also have a racer reference in our loop called racer, which references, at various times during execution, objects of all of the subclass types. When we send a message to a variable reference of the superclass type, the code that will execute is determined at runtime. If the variable references a subclass object, and the code has been overridden in the subclass, it is the subclass code that will execute. This is called dynamic binding, meaning the code is bound to the call dynamically at runtime. I hope you found this example helpful. I know inheritance, polymorphism, and dynamic binding can be tricky at first. Keep practicing and it will make complete sense. The code for this example is available in my GitHub repository with a link in the description. As always, have fun and keep coding.